All right, folks. So we're getting to the mechanisms part of the recycling pathway. We're going to discuss transketolase first. We're also going to talk about transaldolase. So transketolase, remember, is used for 2-carbon transfers from the ketose to the aldose. And remember that this is in the pentose phosphate pathway, XU5P is the ketose. And then we also see our R5P or E4P are the aldoses. We always generate a gap and some other ketose. Okay, that could be F6P or SU7P as products. Okay, now the way this works is a very fascinating thing. I love to talk about this. Transketolase is a cool enzyme, and the reason it's so cool is because it requires a cofactor that makes all the magic happen. And a cofactor is typically some sort of a molecule that's required for the function, but is not necessarily consumed by it like a substrate would be. So the cofactor here would be what we call thiamine pyrophosphate. Or TPP. This is derived from vitamin B1, which is thiamine. And you'll see that on the back of labels all the time, right? Vitamin B1, B vitamins are all used metabolically. And thiamine, and specifically TPP, have this strange heterocyclic aromatic ring. And this is where all the magic happens with ketolases and any kind of alpha decarboxylase. We're going to see lots of these as we go. But this particular guy is very interesting. It has a full aromatic ring, 2, 4, 6 electrons in the pi system. And so this is fully aromatic, but we also carry a positive charge. And we've seen that before with shift bases. We've seen it before with NAD and NADP, all that kind of stuff. But the important thing about this is that this positive charge is unstable. And if we're able to give electrons back like this, we are going to be in a much happier place in some ways than when we started, okay? But we have to be able to do that. And that means that we have to typically be able to push electrons out of that position. And this hydrogen's kind of in the way. And so what often happens to start this out is we actually pull off those hydrogens first. And I don't want to confuse you with this. So we're going to pull off that hydrogen, and we're actually going to end up putting it on a carbon. So we actually have a localized sp2 lone pair, and that typically would not be very favorable. It's an aromatic hydrogen. Those have pKa's ridiculously high for a physiological condition to handle. But the reason this is allowed is because we now form an ionic attraction between our neighboring positive and our negatives. This is called the ylid form. And this would be our neutral form, okay? The ylid form is our important piece. This is our nucleophile. And we're going to use that to attack the ketose. Okay, so I'm going to draw up our xylose 5-phosphate. And I'll draw up our ylid form of the TPP. So what we're going to do first is we're going to attack. Okay. And we're going to generate our TPP adduct. Adduct means stuck on. And our ring is now connected to our substrate. Okay. Now, this is reversible. If we just pulled the hydrogen off, we could push it back off, and we're going to see that at the end. But at this point, it's important to note that we want to be able to push that arrow onto the nitrogen to get rid of the positive charge, okay? That means that we need to push a double bond onto this neck position here, and we can do that by pulling off something here at the alpha position relative to the old carbonyl. I guess this would be a better way to show it. Transketolase does alpha carbon-carbon bond breakage. Okay, so here at alpha, we're going to be pulling up the hydrogen, forming a double bond. Carbon-carbon bond is going to break and swing up, and then we're going to end up landing on that nitrogen. Nitrogen's electronegative, so it loves the electrons, and it's super happy. Now, the old stump down here is going to become our gap. Something very similar to this happened in the aldolase mechanism, but we're also going to end up with the TPP thing stuck on to our substrate. Now nitrogen's happy, but in some ways it's very unhappy because now it's not an aromatic ring anymore. It's actually anti-aromatic. I guess we have there's a lot of electrons here in the system here, right? Where you have sp2 here, it actually technically is aromatic because watch what happens when we push one single pair. Okay, we push this pair down, we push electron density out. And remember, if it's aromatic in one form, it's aromatic in all forms. So we didn't lose aromaticity in the way we did with NAD or NADP, but it's important to see that we still have the same kind of unstable ring where we push electron pairs around. And now we have a nucleophile. This negative charge is now our nucleophile. And then we're going to attack the aldose here, okay? So we're going to be using this nucleophile, and we're going to be attacking our aldose. In this case, that's going to be ribose 5-phosphate. This is our transketolase in the first reaction. So we're going to be using that nucleophile, that new carbanion nucleophile. We're going to tack here, and we're going to grab a hydrogen. Now, the important thing here is that this old carbonyl becomes a OH, and it goes left every single time in transketolase. That old carbonyl always goes left. So not only is this a 2-carbon transfer, but it also makes left-handed chiral centers. So pro-S chiral centers. Okay. So I'm going to redraw this on the next slide so that you guys can see what ends up happening here. So we have our transferred piece on the top. Here's our ring. Our TPP ring is going to be right there. Still stuck on there. Here's our old carbonyl. It went left, and then it used to be ribose, so it was all right all the way down. Okay. And then to finish our reaction, we just need to push off that TPP. And we form our final product. The 7-carbon sugar cetoheptulose 7-phosphate, or SU7P. Okay. And we also made a gap earlier. Okay. So I want you guys to try something. Transketolase 2. Happens twice in the recycling pathway. It goes ketolase, aldolase, ketolase. Remember that transketolase always works with cellulose 5-phosphate. Second one is going to react with erythrose 4-phosphate. For the recycling. So I want you guys to show me the mechanism for how the second transketolase goes. If you wanted to pause right now, that'd be fine. You can try to work it out and then come back to me when you're done. I'm just going to work. So here we have our ILID TPP. There's that pair. We're going to attack it. Hydrogen up. We now have our TPP adduct. There's our OH. We were left, right. Base is going to come in. Again, this is how we make our gap, which is always a product here. Pull off that hydrogen at the alpha position. Carbon-carbon bond is cleaved. Push up onto the nitrogen to kill its positive charge. Now we have our gap. And we have our TPP with the 2 carbons attached to it. So we're going to push through. We're going to attack here, grab a hydrogen. Remember which way that old carbonyl goes? It always goes left. Okay, so old carbonyl goes left, and then we have right, right. We're almost done. We just need to kick off that TPP now. We've done the transfer. Once the transfer is done, it's over. So we're going to pull out hydrogen, make the double bond, kick off the illid TPP, and we'll have recycled our TPP for the next round. And then we're going to have our fructose 6-phosphate. Left, right, right. There we go. So that's transketolase. The next video, we're going to do transaldolase together. Transaldolase is very similar to what we saw in glycolysis, but instead we're going to be doing 3 carbon transfers. Okay, see you then.